Hello and welcome to video 1.1, Speed, Velocity, and Graphing Motion in One Dimension. First question that we have to ask when we're talking about motion in one dimension is, says who? In other words, we need to talk about frames of reference. By frames of reference, what I'm referring to is whose point of view are you looking at? Or from whose point of view are you looking at the motion? And by point of view, for example, if we take a look at the picture here at the bottom, if you're sitting in a train and the train is moving along the tracks, and let's say that we're back here in this window here, and this person sitting in the next set of windows starts to move, and they're walking down the aisle. Relative to the train, you're going to say that they're walking at a regular pace. However, if you compare their speed to the speed of the ground as the train goes zooming down the tracks, they're going to be traveling at a much greater speed because relative to the ground is not moving, the train is moving, and the person's moving. So when we look at the frame of reference, the point of view is super important, and that continues to be true, will continue to be true through the entire study of kinematics that we're going to do. So frames of reference, point of view, where are you referring to? This is even true in our everyday lives if we don't drive in trains, or ride in trains rather. For example, are you moving as you watch this? Chances are, relative to your computer, you are not. You're sitting still. However, relative to the sun and the moon, yeah, you're definitely moving, and you're moving pretty darn fast also. It's important to understand where our frame of reference is because not only at slow motions like those that we see in everyday life, but especially at the faster speeds, as we get closer to traveling to the speed of light or having objects travel at the speed of light, then where you're at looking at things becomes even more important. So one of the things that we will be keeping in mind throughout this unit and continuing through the year is says who. What reference are we talking about? Whose point of view are we looking at? The second question that we need to ask about when we're talking about motion and trying to figure out as much information as we can is how far? There's two different things that we need to think about. There's two different words that we use in science that we need to know the difference between. One is distance and the other is displacement. If we're talking about distance, let me just split the screen here a bit. If we're talking about distance, distance then is the amount of space that has been traveled through along the actual path. So it's answering the question, how far, again. So it's the amount of travel along the actual path. So in the picture down here, our distance, we start at the 0 point, we travel east 70 meters, then we travel west 30 meters. So in this particular case, our distance is 70 plus 30, which is 100 meters. We are talking about asking the question and answering the question, how far did we go? What's our total distance traveled? Oftentimes, however, we aren't interested in distance. We are more interested in displacement. How far did we end up from where we started? So displacement is not along the path of travel. Displacement is the distance between the start and the finish point in a straight line. So in other words, again, we come back down here to our picture. This blue arrow is going to show us that from where we started to where we finished off is only 40 meters. So our displacement here is 40 meters. And typically when we talk about displacement, we call it a delta x. And displacement, if you need to figure it out in terms of your given information and not a graph like this, then delta x is equal to x2 minus x1, where in our picture here, our x2 is our larger value. That's what we started with first. And then our x1 is what we ended up with. Now, how can we determine this and how do we figure this out? Because if we had switched this and we had said 70 meters was x1 and 30 meters was x2, our displacement would not be a positive number. It would be a negative number. And we can't ignore that here. The easiest way to figure out what to do and whether it should be a positive or a negative number is that you have to determine and you have to pick out a positive direction and a negative direction. The easiest way to do this is to go along the lines of how graphing works, in which case, if you are moving in the positive direction, then you will have a positive displacement. So we usually assign positive to go with the positive x-axis. Or it could be the y-axis if you're going up. So if you're going up, positive. If you're going to the right, positive. If you're going down, would be negative. If you're going to the left, it would be negative. It does not have to be this way. This is just the norm, okay? And so you assign the positive to go with the positive x and y axes. You assign negative to go with the negative x and y axes. It's a convention. As long as you stick to it, it will make sense. Is the best way to show me what you've chosen to be positive and negative is on a problem, you can just put a little set of axes like this, a little origin, and just say plus, plus, and I'll know that that means that you are saying that up is positive displacement and to the right is positive displacement. So again, distance is the total distance you have traveled, the total length that you have traveled along the path. It doesn't matter if it's straight, if you turn around, if you go crooked, if you overlap, it's still the total amount you traveled. Whereas the displacement is the difference from where you started to where you finished. And it doesn't matter how you get there, I just want to know what did you do from start to finish, how far away did you end up from where you started. Okay, so now we know how to ask the question about whose perspective are we looking from. We know the difference between distance and displacement, so we can say how far we've gone. And this leads us to the most important question, which is, of course, how fast are we going? How fast are we going can also be answered in two different ways, just like how far did you go can be answered in two different ways. The how fast you can go is going to be answered based on speed or velocity. Super important you understand and remember the difference between these two terms. Speed is how far an object can travel in a given time interval. Okay, so it's how far you can travel in a given time interval. If we want to calculate this, then we would say that speed is our distance over our time. Again, notice that it's distance over our time. This is what we call a scalar. It means that it has magnitude only, magnitude being size. So for example, 100 miles per hour, 3 million meters per second, things like that. So if we take this word equation, speed per distance, and we change it into a formula that we will be using, then V is equal to D over T. Typically, we will have speeds in meters per second or kilometers per hour. We rarely do meters per hour or kilometers per second, sometimes, but not often. So if we just want to know how fast someone's going, we don't care what direction they're going in, then we can find out the speed. We'll get into average speeds and instantaneous speeds in a minute, but for the moment we just have speed. We can also answer the question with how fast someone's going by asking about the velocity. And velocity is speed in a particular direction, meaning that speed is not distance per time. Sorry, velocity is not distance per time, but velocity is displacement per time. Now, notice that because it's displacement, and displacement takes into account a direction, the one thing we have to keep in mind is that velocity is not a scalar quantity, it is a vector, which means that it has magnitude and direction. So if you are asked to give me the velocity of an object and you tell me that it is traveling at 100 kilometers per hour, you will not get it correct because that's its speed, not its direction. You have to tell me where it's going as well as how fast it's going. The abbreviation for velocity is displacement over time. Is v is equal to delta x over delta t. Now we typically say delta t because it is a time elapsed. It's a time period that we're looking at. However, the vast majority of the time, we are looking at from time equals 0 to a certain ending point. So then the delta t, which is t2 minus t1, the t1 is 0, so it just becomes a time. However, because we can look at velocities and speeds at intervals along the path and along the motion of the object, we really need to keep in mind that it is, in fact, a delta x over delta t. It, too, has the same units as speed does. Their abbreviation of v, I tend to write the v as a lowercase cursive v as opposed to just a v, because we use v for lots of things in physics, and it's easier for me to keep track of whether it's a velocity or not if I use a lowercase cursive v. I would suggest you come up with some sort of a abbreviation like that as well to make sure that you know the difference between the two. So speed is distance per time. Velocity is displacement per time. They both tell us how fast, but oftentimes they can give us very different answers depending on the situation. To better understand what this is talking about with frames of reference, distance versus displacement, speed versus velocity, we like to graph things, we being physicists. So graph it to understand it better. Let's take a look at this graph here. This particular graph is of position versus time. So we could give it the title of, this would be a bad title, but we could say x versus t if we wanted to. And we take a look at the object, and we can tell that its position is changing at a constant rate because it is a straight line. If the position is changing at a constant rate, then what we want to be able to look at is we want to be able to look at that slope of the line and figure out what is that constant rate. So then we are interested in the slope. Now remember that the slope is the change in y over the change in x. If we pick 2 points, as is done here on the graph, our change in y in this particular case is a change in distance, so it's a displacement. So for here, our slope is going to be equal to delta x, which is 11 meters, over our change in x, meaning the x-axis, remember, which in this case is delta t, which is 1.0 seconds. So the slope of a position time graph in this particular case is 11 meters per second. And we said that according to the variables on our graph, this slope is delta x over delta t. But wait a minute, let's look back here for a second. We just said over here that delta x over delta t is velocity. If that's the case, and the slope of a position time graph is also delta x over delta t, then we have a really cool relationship going here, that the slope of the x versus t graph is velocity. Super important to understand. Because oftentimes in physics we graph our data, we graph observations that we've made, and if we're starting with position time, you can graph it, you can find out what the velocity is. You can find out if the velocity is constant or not. In this particular case, our velocity is constant because the position is changing at a constant rate. So these are two ways to keep thinking about velocity. Number one is that it is the slope of a position time graph. But even more important than that is to internalize the fact that that velocity is the rate at which position changes. Okay, it's the rate at which position changes. Our rate does not always change constantly, and in fact, sometimes it doesn't change at all, or sometimes it changes very rapidly. And in those cases, we still can take the slope of an x versus t graph to get velocity, but we have to have more than one because it's not necessarily the same. This leads us to instantaneous versus average velocity. So if we take a look at these two graphs, the top graph is velocity versus time from 0 to 0.5 hours. The second graph is also velocity versus time in 0.5 hours. However, these two objects are doing something very different. If we want to first explain what instantaneous and average velocities are, we can then understand better what we're seeing in the graph. So instantaneous velocity, as its name suggests, is the velocity of an object at one particular instant. Now, if we take a look at the first graph, the top graph, the velocity per time, if we take any particular instant along the line, its velocity is all going to be the same. The velocity is going to be 40 kilometers per hour. So the instantaneous velocity in this case is not very interesting. It's the same all the time. However, if we look at the second graph, our instantaneous velocity here is different than our instantaneous velocity is here, or over here, anywhere else on the graph except for its partner position when it crosses the line again, is going to be different. So the instantaneous velocity of an object can be the same as the speed that it's going at. It can be the same as the average speed, or it can be something completely different. It all depends on what is going on. If we look at the average velocity, we are really looking at what is the overall average velocity of this object. It's not at any particular instance. This is an overall view. The first graph, it doesn't change. So this is the average velocity. The second graph, however, the velocity changes a lot, and you would have to do what we call a weighted average to find out the average velocity. You'd have to say how much time was it at each one of these time intervals, find out what the velocities were and how much to put it in, and then you can come up with an average velocity of, as they have here, of 30 kilometers per hour. So in this case, our average velocity is gotten from a weighted average. And you can get this two ways. You can get it from the graph, from saying, all right, I'm going to figure out all of these at, say, 0.05 hours, figure out what the speeds are, and then average them up depending on what they're doing at each. Or you can, if you know more information, you can find out the total displacement traveled by the object. And then from the total displacement traveled, you can then, and the time gone, you can then figure out the average velocity. If you do not have the displacement values, you don't know any more information than this, then to get the average velocity, as I said, it's like a weighted average. What you are really looking for is you really want to be able to do and use the equation that the average velocity is final minus initial distance over final time minus initial time. Same thing as what we've had before, delta x over delta t. But in this case, the deltas are not necessarily going, the x's rather, are not necessarily going to be the first and the last. Similarly to the times, because we might need to do it at this interval and then T naught is not 0. T naught is about 0.05, and T is about 0.17 or 0.18. So the naught means initial. The things without subscripts means that they are the finals. So if we put this together, if we take a look at the fact that we can distinguish between displacement and distance, between speed and velocity, and now we know that we can look at instantaneous or average velocity, and we want to see how this all comes together and what it looks like, we can look at a position versus time graph right next to a velocity versus time graph, and they actually correspond to each other, and we'll see what the relationship is. So if we look at these two graphs, the position versus time graph is in red on the right, and the velocity versus time graph is in green on the left. The velocity versus time graph has an object with varying velocity. Obviously, its velocity starts at 0, and at about 15 seconds, it is up at 15 meters per second. It stays at 15 meters per second for 5 seconds. It then decreases its velocity to 5 meters per second in 5 seconds, and then it stays at a constant velocity again of 5 meters per second for 5 more seconds. So this here has a varying velocity. Okay, its velocity varies. Over here, when we look at the displacement versus time graph, we can see that the velocity is varying by noticing that the slope of the line shown is not a constant. Because remember, the slope of a position time graph gives us velocity. If we want to find the instantaneous velocity over here on the left graph, then we would have to take the tangent line at every point. Now, you may or may not have come across tangent lines in math. It's not super important at this point. The way that we would determine it is we would say, okay, if I want to find the instantaneous velocity there, I'm going to say it's 15 meters per second, and that's its instantaneous, velocity. Down here, I would say it's 5 meters per second, okay? When we get to position time, though, and we want to be able to create a velocity time graph from our position time graphs, we actually need to look at the tangent lines because, again, remember that velocity is the slope of x versus t. And that's because the slope is delta x over delta t. To get the slope of a curve, we have to take tangent lines. Tangent lines are lines that only hit the curve at one particular point. So we can pick points like they have shown here on the graph on the right, and we can find their change in x, meaning change in position. We can find the change in time, and we can then find the slope of this point here, and we can plot that here. So we can find instantaneous velocities from position time graphs. I'm going to call it Vn for instantaneous velocity. If we think about this some, if we know that velocity is delta x over delta t, then that means that we can rearrange this equation of v equaling delta x over t to be that v delta t is equal to delta x. Velocity times time is displacement. That makes sense because displacement over time is velocity. If velocity times time is displacement, then, that means that we are multiplying two dimensions together. If we take a look at the graph on the left, we can then take this information and use it to our advantage. Let's say for a minute that I want to look at the time period from 0 to 15 seconds. I'm looking at what's going on here. I can find the slope of the line. That would certainly be beneficial to me. but I can also find the area underneath the curve. If I look at the area that I just shaded in, I hash marked in there, underneath the velocity time graph from 0 to a, notice that I get a triangle. And the area of this triangle, remember the area of any triangle, is 1/2 the base times the height, right? Well, in this case, 1/2 the base is time, and the height is velocity. Oh, look at that. I was looking for velocity times the time. Velocity times time gives me displacement. That means that if I find the area under a velocity time graph, I'm going to get displacement. So area is equal to delta x because it is equal to velocity times time. Now, yes, in this particular case, we have a 1/2 there, and that 1/2 does have to stay there because it's in the shape of an area. I mean, it's in the shape of a triangle, but it does not change the units associated with this. This works all the time. I could also find the area from B to C to find out how far did my object go in this case. And to do that, I would simply cut my shape into two, and I would say that I had shape 1, which is a triangle, then I have shape 2, which is a rectangle, a square actually, and I could add up those two areas. So this is pretty cool because what it means is that I can take the slope of a position time graph and get velocity. It also means that I can take the area under a velocity time graph and I can get displacement. So automatically you see that there's a relationship here between position and velocity that unless we graphed it, we would not necessarily see. And it wouldn't be as meaningful to us. Now, if you're in calculus, you will come across this relationship multiple times. It is an integration or a differentiation, depending on which way you're going, from position to velocity or velocity to position. If you're not in calculus, don't worry about it because you don't need to know it. But one more time then, the velocity is the slope of a position time graph. The displacement is the area under a velocity time graph. So just by knowing one set of information, we can come up with the other set of information. So why is this important and what are you going to do with this? Well, because we now have the ability to find velocity as delta x over delta t, either by using it from the slope of a graph or by solving problems dealing with using that equation. We can also rearrange the equation to find displacement by finding v times delta t, either by finding the area of different parts of the graph underneath it or by using the numbers, okay? And also don't forget that the difference between speed and velocity is that velocity has to take direction into account. So in this case, with your velocity decreasing, they're still going in the same direction, they're just slowing down. Here they're speeding up. Here they're traveling in a constant speed, they're slowing down, and then they're traveling at another constant speed. None of this means they have changed their direction, though. So what do we do when we want to solve a word problem that has information in it that we're not sure, and we're now getting into equations that we may not know exactly which one to use? Well, we have a series of steps to use to figure it out. And this is the same set of steps that we'll use throughout all of your problem solving. First thing, read the whole problem. You may need to read it more than once. Chances are, as we move on into the more difficult stuff, you're going to need to read it 2 or 3 times. Decide on the object's importance. Sorry, I forgot the word if. Decide on if the object is important and what the time interval is. Okay? So what object is moving that's important, and for how long is it moving? Draw a diagram. Always draw diagrams. I will constantly be reminding you of this. Draw diagrams and choose the coordinate axis. Write down your known quantities and then your unknowns. And I don't mean write it down in long words. I'm talking about something like V equals 2 meters per second, T equals 1 hour. Those are my knowns. And maybe my unknown is what is my displacement. I would write it like that with every problem. Then my question is, well, what equation do I know, or equations do I know, that relate my known quantities with my unknown quantities? And are they valid for this situation? And if so, what should I use? Once you've picked your equation to use, then you're going to do what we call the plug and chug. You're going to plug in your numbers and chug through the algebra to get to your answer. Round to an appropriate number of significant figures, and we'll get to significant figures in more detail as we move on. But right now, if your calculator gives you an answer that has 15 decimal points, chances are that's not what you're going to want to use. And you're going to want to round. Until we get more into significant figures, I would say round to 2 or 3 decimal points. Sometimes you have to do some algebraic manipulations before you can get to the plug and chug, but you still eventually will get to the plug and chug. And I would strongly recommend here before you plug in your numbers, to move around and redistribute your equation first. So once you figured out the equation, then manipulate it. Manipulate your equation to solve for the unknown variable. Then do the plug and chug. Because if you manipulate it first, it's much easier to go back and fix it if you made mistakes later. Lastly, look at your results and say, does this make sense? If you're trying to find the speed of an object and it came out with a number that's huge, then chances are you have made a mistake in your calculations. Last but not least is check your units again, make sure that you have put them on the answer, and make sure that they are correct. So with this information here, that gives you a brief introduction to the differences between speed and velocity. Also introduces you to the fact that by graphing your data, you can go back and forth between speed and velocity and distance and displacement, and you get lots of good information from it. So bye for now.